Thank you very much indeed for a most exciting paper on how to measure and fabricate interesting supports for your panels. As with the first session this morning, we will take questions at the very end of all this, and therefore I will invite the next speaker, which is Christina Young, on behalf of a research project by Christina Young, Britton Yu from the National Gallery we heard this morning, and Ray Marchant. And they've been looking into experimental evaluation of the adhesive and filler combinations for joining panel paintings. Please, Christina. You were there. Yeah. That one's there.
I'm going to talk about some research that really started in 1997 with Ray and Simon Bobak at the EB Street Studios with the... Just get this working first. Right. With the research that they were interested in because of the issues they had with the panels they had to deal with. I'm going to concentrate on just 4 areas of the research that we've been doing. The rest will appear in the preprints. With the handling properties, hardness, adhesion of the wood, cohesive strength and drying stresses I won't deal with today specifically. But I'm going to deal with the stiffness compared to the wood around the gap filler, the strength of that gap filler, the stability of gap fillers, and particularly to do with contaminants when gap filling panel paintings. These are Ray's early studies in 1997 when he started to look at the alternatives, what was around commercially for gap filling materials. A lot of these are conservation grade materials, but as he found, and I found subsequently, very unsuitable as gap filling materials. But these are his first empirical tests looking at the hardness by simple fingernail testing and thumbprints as he's first starting the empirical tests. And then adhesion to the wood by looking at the different adhesion properties, just simply by applying them onto the wood sticks and seeing how well they stuck. And then, all importantly, drying stresses within a structure, looking first how they how they dried in plane and out of plane, and how they might pull up. Oops, sorry, get this one. That's it. How they might pull up if you had a thin balsa here was put here instead of the gesso, but to see what would happen if you pulled up as they dried. I became interested in this really when I went to the Courtauld and worked on panel paintings in our studios with our students because we had a certain sort of panel regularly coming through our studios. Just to show this slide, that we also got the same issues to do with modern adhesives, a lot of them with no coherent strength at all. This panel, in fact, the one that Alan Miller worked on when he was at the Courtauld, came to us as a triptych from the National Trust property with the composition slightly changed from its correct position, which is its composition as it should be here. The problem it had when it came to us, that it had been restrained in its frame due to environmental changes and was splitting. We took it out of its frame and it came to these 3 parts here. These were the rector of those 3 panels. That's where our interest... A lot of the panels we see are thinned panels going back into semi-controlled environments. Another case for us more recently with this panel from Therese National Trust property in Cornwall, attributed to William Seeger from approximately thought to be 1600. Again, tangential cut oak panel that had been thin to 5 millimetres thickness. In the past, it had had splits repaired. You can actually see in this diagram at the bottom here, these are the original splits that have been prepared with a phenolic adhesive called Cascamite in the UK, or now called Extramite. This time when the panel moved due to failure of the heating conditions, so the RH went down, to 30%, this panel tried to move and hit the frame, and the original plank joint split along the hide glue original joint instead, taking away some of the original paint. So these are the problems that we see, just to put what I'm going to talk about in perspective for why I'm looking at this sort of gap filler. Here is the panel in our studios being prepared at the time using the method that Ray uses, and Ray came at the time to come and work with us with this particular panel. So the scenario that I was particularly interested in is a gap which couldn't be rejoined without some sort of filling, whether there was room for a fillet or not. In this case, most of the time our panel splits had gaps around 2 millimetres, 3 millimetres maximum, so a gap filling adhesive was required. Our panels were also always automatically going back into uncontrolled environments where microclimate chambers weren't wanted and only some form of auxiliary glazing and sometimes backboarding was allowed. This is the house in which that panel belongs in. and is now back in. So the criterion for me for this work was that the test that we did would look at the painting and the gap filler in the mode in which it was actually going to be in reality rather than in some artificial situation. So I was interested in its load-bearing properties and the modes in which it would be in the panel as it deformed, allowing for some deformation without failing within the gap filler, that no damage should happen to the original materials of the painting if fracture occurred in the gap. Obviously, a workable consistency was essential, stable and removable. These little samples, they're not panel paintings, but they're the nearest we can get with some representative samples, were small oak blocks, which approximately, the oak was about 150 years old. It was in the National Gallery wood store. They were cut, approximately radially cut, because this is real wood. In our case, these weren't perfectly radially cut, and they were joined with these simple blocks here. All the gaps were 2 millimetres in width, as you can see here, and they were aged. Some of them were aged at 60 degrees C and 55% RH. Some were naturally aged. There's a big debate could be had about thermally aging above the glass transition of most of these adhesives, but I think that's really for another discussion at this point. I can show you the results of both, and you can make your own mind up about the validity of that approach. All these panels were then conditioned at 55% RH before testing. The choice of test for this was, as I said, basically because I wanted to be testing in the mode in which a panel would really be in, or at least one of the modes a panel could be in. If, for instance, it moved due to humidity or moisture changes within the panel and the environment around it. So in this case, by doing what's called a 4-point bend test, you can see the little block in here, which is our mini panel, the join and the wood experienced the same what's called bending moment around the rollers. In this sort of test, you can also see which fails first, whether it's the wood filler or the wood itself that fails. So we're not adopting an ASTM or ISO standard for this. The normal test for this sort of gap filler would be a shear test, which has been done in the past and is valid. But I felt for this I was interested to see how these would perform in a more realistic scenario. Also, a lot can be gained by watching it, just as with a real panel. The type of bending that occurs depends on the stiffness of the adhesive relative to the particular wood or the condition of the wood we had. This wood was naturally aged, but it didn't have any wormholes, so it had structural integrity. So these tests are relative to what we're looking at, but I think that's part of the point about doing things that are realistic. In this case, if the joins are very small compared to the volume and the amount of wood, so the proportion of the join that's under load is very small. So when the glue or the adhesive from gap filler is very stiff or the same stiffness as the wood, you get this bending. And you'll see as I show you other slides, you get this curvature as the wood bends around the rollers. When the adhesive isn't very stiff compared to the wood, you get this triangular shape because basically all the bending's going on in the adhesives. At that point, you think, that's no good for my panel, but we still carry on the test because we want something that behaves like the panel. So this is an example of one of the tests here at the point of fracture. This is one of the adhesives here. This is probably the beaver test, actually. The point about this test is the way it fails tells you about the practical limit of what might be expected in a panel in extreme conditions. And I'll show you, put this in perspective in a minute in terms of these tests. We're also able to tell the failure mode and the type of failure that's occurring. So whether it's a cohesive fracture in the gap filler along the centre here, an adhesive fracture where it's happening between the gap filler and the wood itself, whether it's ductile, so it's a gentle failure, or brittle, in this case at the wood interface, or in this case in the wood itself. So it gives you an idea about what can happen in these situations as well. The data that comes out of these sort of 4-point tests measures the load versus displacement and the peak bending load before failure of either the gap fill or the wood. This again is the sample in the little roller blocks. Here comes the graphs, okay? I talked through these slowly. I haven't got too many of them, but I think they're essential at this point to explain what's going on. This is looking at the resin W that was mentioned earlier this morning by Britta, which is a UK PVA with a mixture of coconut resin, coconut flour and microballoons. Looking at it at different thermal and natural aging periods. So this measurement here is negative because we're measuring compression. This is the displacement, and this corresponds to this displacement here is this displacement here. So in the case where the PVA is relatively new, you get a ductile failure. As it starts to age, that becomes progressively more brittle. And in the final case, in this case for the 470 days, you're getting failure of the wood, which is a more failure of the wood and the gap filler at the same point, a more brittle failure, and in this case, thermally aging, it was snapping of the wood. So the graph tells you the kind of failure you've got by the degree of plastic deformation before complete failure. As you can see here, this displacement here corresponds to the blue line. So at about, say, 6 millimetres is where it starts to fail. That would correspond to this panel having 6 millimetres deformation about 30 millimetres from its centre. That might seem quite a lot, but this particular panel actually did that in natural conditions. It would go from 55% RH, as it is here, what's been worked on. If we took it down by 10% RH, we'd see massive changes in the panel constraint. So for panels that are moving a lot, these numbers aren't too unrealistic. I'm just going to backtrack 1 minute to the research that we started in 1999 and then wrote up in 2002, looking at the combinations of gap-filling filler materials you could use. We looked at lots of different things, but I'm going to concentrate on the resin W, coconut and microballoons. So here we have the data where we use the resin W, just the coconut, to see exactly what it does do to the filler combination. This is down here, just the peak load. I'm not looking at stiffness, the peak load of failure of those little blocks or the gap filler in that block. And as you increase the amount of coconut, you can see the peak failure load goes up. If you put an awful lot of the coconut in, you're actually where you're the wood snapping instead of the gap-filling material snapping. Again, if you look at just the resin W with the microballoons, it produces a much more crumbly mixture in practical terms, and you get less, a less strong join. And then you have the combination of the two, a 1-to-1 mix of the coconut and microballoons within the resin W gives this value. They look almost the same. The difference is the applicability was actually much better. It was easier to use this material than to use just with the microballoons. And in both cases, you get ductile failure. These samples were at the time of 30 days old when they were tested. This is with a larger combination with more filler mix in with the resin W, and here we got failure of the wood. The wood failure happened either at the interface or within the body of the wood. For this part of the project, which happened, I guess it was another 3 years later when we started looking again at these, we obviously want to look at how they aged and some other issues to do with contamination, because we haven't got perfect joins in panels, and we need to have a look at that as one of our particular issues. So we stuck with our resin W, which is used in the UK. Molith DM427 seemed like a possible option at the time because its aging properties hadn't been established and it was supposedly a good replacement for DMC2. Jade, because it's used in painted conservation, I felt it'd be not stiff enough. It proves that it isn't, but it was nice to have at least something that was supposedly stable. Araldite, which George introduced us to, and we started to use it, being more used in the UK now, and hide glue as a contaminant as well as a filler. And the fillers that we concentrated again at just looking at the relative properties with these particular fillers. So the microballoons, these are spherical balloons of 50 microns diameter, and the coconut flour, which is basically ground and sieved coconut husks. And the filler that's already in the EVA is silica, titanium dioxide, iron oxide, and a phenolic resin. So these are the combinations that we tested. There was the two mixtures, as I said, and then 1-to-1 mixtures of those two, weight to weight, 1 gram of that within 5 millimetres of our resin W. We did that for all those 3 adhesives, and then we used the Araldite as per the instructions, 1-to-1 part, as it has its filler already in there. I was going to talk about the stability of these particular gap-filling combinations. So this data is when we've used them as gap fillers. So the blocks themselves were tested after mixtures of different agings. We'll concentrate. This here is the stiffness, which is the blue blocks, and the pink is the peak load at which something failed. And you can see there's a general trend. This is for natural aging of this increase in stiffness with time and the increase in peak load before failure with time. This is also data from our first set, just to see how reliable our data was over time. This is a completely different set of blocks and adhesives, and there's quite a good correlation, which gave me a certain amount of confidence about what we're trying to do. And then that's compared to the thermal, well, not compared, but as well as the thermal aging showing the same trend. So although you may feel that thermal aging of these particular materials isn't valid, it is showing the same trend. Therefore, there's a similar mechanism is going on, and there's a useful way to get very long extended periods of aging. Okay, this is the EVA. Not surprisingly, as it cross-links on curing, we didn't expect it to change, but it's just nice to confirm that for the natural aging and thermal aging, it is staying stable. These large error bars, due to the fact, because you get brittle failure, you get a very big variation in the way and how it fails. That's natural with the fact you have lots of energy in the failure mechanism. So that gave us what we expected. The DM427, which I was quite upset to see these results, doesn't stabilise at all for these 60 days and for thermal aging. In fact, at the moment we don't have samples to show at what point it stops changing. So this is again showing for thermal aging here, this is stiffness going up, and for peak load, the peak load is going up. So that's thermal aging and natural aging showing the same properties. And the jade, we only did 2 lots of times for these because the jade just was really too stiff and we didn't carry on the experiments. Compared with all the other data that's also available for jade, it kind of shows it's all kind of stable. There's not many data points to be consistent, but with other data around, it shows it's stable. So just comparing these with our original results with the mixture, 1-to-1 mixture, and after 470 days of natural aging, the stiffness increase that's going on due to the fact the lack of stability of the resin W mixture itself. And actually, I know Alan, Phoenix and I've been talking about, he has data for DSC testing of resin W to show that there's a similar trend in its change in properties, even though the formulations are continuously changing as well. And then just to put this in comparison, if we look at the epoxy 1253 over the same test, we see that that's how stiff it is. And because it doesn't change, this is what you get for all values of it. So it's a lot stiffer than, say, new resin W, but actually when it comes to aged resin W, there's not that much in it. As against the DM427, which is still, although it's still changing, isn't as stiff or as strong, and the jade, which is relatively weak compared to the wood that we're looking at. So this is where I stick my neck out a little bit, I think. This is our average wood failure for our samples that we've been testing and the data that I've just shown you. My question is, at what stiffness should we have these gap fillers? Are we trying to match the wood? Roughly, the stiffness of the wood from our tests, when you calculate the numbers, is around this area. So both these materials have roughly the same stiffness of the particular wood we were looking at. The jade really just isn't stiff enough. The DM427, not stiff enough either, really. And again, what's the best load to failure for these materials? Is it just below the wood value? Our wood range went from about 90 to 160. Should we just have it just below the wood value? Well, if that's the case, then both these adhesives in that extreme case are too strong. So this is just to summarise what I've said at this point. So basically the jade really didn't offer us any opportunity as a gap filling material. DM427 possibly for very small panels, although unfortunately it's unstable. And both the epoxy resin and the resin W have good stiffness, but can cause in these particular sorts of situations wood failure if there's extreme movement of the panel, of our little panels. I'd just like to talk about the contaminants that we looked at, assuming here that there's either residual varnish or possibly other consolidation materials left behind in the join, or it's a partial disjoin and you don't have the ability necessarily to route it out or to clean it, or you decided not to. How does that affect or compromise the gap-filling abilities of the combinations we looked at? So we concentrated on 4 materials, beaver, damar, hide glue and Paoloid B72 as our contaminants within the sample. Just down here is the sample itself. So this is our wood block. The contaminant was brushed on either side, and then the filler was added later. And after 30 days, these were tested at 55% RH. I'm just going to concentrate on the resin W and the epoxy 1253 here. We have the B72 as the contaminant, the damars as contaminant, beaver and the high glue, then compared to without any contaminant, and the same for the resin W. What we can see here that with B72 compared to when it hasn't got any B72, we've actually increased the strength of the joint, and that's consistent with data that Jerry Padani produced in 1992, showing that basically B72 didn't compromise wood joins. He did it by shear test, a slightly different test, but it's consistent with that data that it's actually acting as a very good, effectively as a wetting agent rather than contaminant in this case. And the same for, can be seen also for the high glue. Again, you're getting it's acting as a good wetting agent. As against the definite compromise of the joints with the damar and the beaver. And the same is true also for the resin W in terms of the hide glue. Basically doesn't change the bond, but it's aqueous. It's not surprising. It probably rehydrates as you add the resin W to the hide glue. The beaver and the damar both compromise the join, and the B72 seems to slightly compromise the join. The same was true when we tried this on hairline joints, just to compare. We got the high glue and the B72 increasing the strength of the joint against the Damar and the beaver, which compromised the joint if they're there as contaminants. I'm not going to show that, because that's what I've just said, but I'm going to concentrate on something else I think is probably more relevant for today's conversation. This is the panel that we have at the moment in our studio to work on. It's the two excise men, probably 17th century panel by the panel makers Marx, which come from an English heritage property which is partially controlled. At the moment we're monitoring the conditions there. At the moment we've taken out its auxiliary frame. Again, it had failed and produced new splits, which you can see just about here. It's gone back. That split's gone again. Another split's produced because of constraint in its frame. So faced with this problem in my studio at the moment, what am I going to do based on my results? Further research is the straight answer to that. From these tests, for this particular panel, I felt that the epoxy, probably, if we could use it with a release layer, might be the option available to us, or maybe weaken it slightly with microballoons. Now, we are going to have an additional panel spray support for this, so you could say, well, the panel's not going to see that amount of movement, so that it shouldn't fail, because you shouldn't be seeing these large movements. But I guess, like any design engineering, you have at least a factor of 3 safety margin in there, and I don't, for the moment, that safety margin is big enough. So I like some way of reducing the strength or being able to reduce my movement in the panel. Obviously, we'll backboard and glaze if we can to reduce that half-life as well. The other thing that I think hasn't really been addressed with any of this talk of panel paintings is fatigue of the joins and the panels themselves and any mechanisms we're making for them. If you're getting small temperature and humidity fluctuations, most of those materials are responding, and I'd like to assess to what degree that may be affecting the joins that we do, the fractures that we see, and that's something we're doing on small scale now, starting to do fatigue testing due to temperature and humidity fluctuations. It's becoming all more pertinent with changes in, or talk about changes in environmental specifications for museums. I'd like, ideally, the magic adhesive, like everyone, which had the similar properties to resin W but was stable. To my knowledge, there isn't anything out there that would do that. I'm also interested in comparing the glass transition of these materials, which, for the ones that are reversible, are too low to be practically useful. But I want to compare that to the ductile brittle transition, which is the thing that causes the damage to the panels themselves. So this is where we'd like to take the research in the future. Wrong one. There's lots of people on here because this work started in 1997 and it's been through these panels being worked on by at least 2 students each and many other people at other institutions, the National Gallery, Simon Bobach student, E.B. Street, and other people at the National Trust have been very helpful and collaborative in all this work, and it's a continuing process. So thank you for your attention.